Welcome to Fred
and Amy's Math Shack.
Today we're going to look at something called the rectangle approximation. My first question for you to think about is what methods could you use to exactly or approximately find the area under y equals the square root of x between x equals 0 and x equals 10. I also mean in between the x-axis, so it's this area here. Have a think, see if you can do any calculations. Well, one thing we could do is we could actually work it out exactly, and that is the integral of the square root of x. That's going to become it's a definite integral. We're going to write it as x to the half, and then we're going to add 1 to the power, divide by the new power, so our exact answer is going to be 2/3 times 10 to the 3 over 2. And if we wanted to work that out as a decimal, we could. (21.081). But some other methods, approximate methods, would include the trapezium rule and also Simpson's rule. I'm going to briefly talk about both of these. I have covered them previously. So here is the graph, and we've worked out the area, but how can we do it approximately? Just going to remind you of the technique more than anything. So if I want to do it, I can right-click it. I'm using autograph here. Find area, and if we use trapezium rule between 0 and 10, let's use 10 trapezia. Then you see we get this, we get 20.89, a bit of an underestimate. We can see we're missing this gap here. If we use Simpson's rule, then we fit a quadratic to it, in fact. These are the midpoints that the quadratics fit to, and we get a really 21.05. Okay, very, very close, just that second decimal place slightly out. So where does that leave us? That leaves us with this thing up here called the rectangle rule. This is rectangle minus, and this is rectangle plus. Now they don't give very good approximations, so why on earth would you want to use them? Well, if we look at them again, rectangle minus, for this shaped curve, all of the rectangles end up being the area below the curve with like missing little bits. So it's going to be an underestimate. If I do rectangle plus, then I use the right hand point in all cases, as you can see. And actually all of the rectangles are above the curve. So the thing we get out of the rectangle rule is, the rectangle approximation, same thing, is that it allows us to give us bounds on integration. Okay, so it's not that it's any more complicated than trapezium rule or Simpson's rule. It's actually much more simple, but it gives us just a different perspective. Let's have a look at a derivation of the rectangle approximation. First of all, going to look just at 4 rectangles where the graph has a positive gradient. It should be noted, actually, I've not said this yet, that the rectangle rule will only really apply effectively when you have no turning points on your curve, i.e. it's just increasing or it's just decreasing, because we're going to be interested in overestimates and underestimates. And whilst you can see over here we have an underestimate, and as soon as the curve starts going down, then it will overestimate this bit, and you won't know overall whether it's underestimated or overestimated because of cancelling out. So we're always going to be interested in just very simple parts of curves. Okay, so we want to find the area underneath this curve, and what we're going to do is we've made these rectangles. We've got A here and B here, and then we're interested in splitting it up into 4 little rectangles. So H, again, as for the trapezium rule and Simpson's rule, would be B minus A over 4. And that means every single width is equal to H. Okay, next bit, how are we going to figure these things out? Well, to get the area of the rectangle, it's just going to be the value of the function times by h for each rectangle. But if you notice on this one, we're using the value of the function on the left-hand side, and this is known as the left sum. Whereas to contrast over here, actually on this first rectangle, we're using the right-hand side, which makes it the right sum. Okay, and then if I label my x coordinates, I'm going to get x0, x1, x2, x3, and x4. I'm just lining it up with these things here. So I can see when I find my first rectangle, this green one here, then it's actually going to be the corresponding y0 multiplied by h. And then if I find the next one, it's going to be y1 times h. And I'm going to be adding these up. And then I'm going to get y2 times h. And finally y3 times h, this one here. Now note, I can actually just factorize out h. And it's going to give me y0 plus y1 plus y2. So bear with me, my pen is failing me here. y0 plus y1 plus y2 plus y3. And we've got a formula for the rectangle rule. It's, it's a bit like the trapezium rule, but it's even simpler. You won't be given this in a formula book, but I hope it makes sense. And it's not that you should necessarily learn it, but hopefully you can see where it's come from, and that we could actually, we can actually now do it really quickly. We can just find the function at all these left-hand points, add them up, and then times by h. That will give us the full area. Now, if we do it for the right-hand sum, this time we're going to be using the point that corresponds with x1 first of all. So we're going to first of all get y1h as my first area. Note, this area here is actually exactly the same as this area. They're this, so you've got these matching areas for the left and right sum. If I do it for the next one, and I'm using the right hand point, it's going to be y2 times h. Then y3 times h is here. And finally, we are using the end point. This time it's going to be y4 times h. And this time I can factorize out the h. And I've got y1 plus y2 plus y3 plus y4. Okay, and every time there's going to be, so this one matches with this one, and then this one matches with this one. There's just two that don't match. Right, that's it. Now we see for a positive gradient that actually the left-hand sum is given an underestimate and the right-hand sum is giving an overestimate. So what we can actually write down is that the left-hand sum is less than the actual answer, which is less than the right-hand sum, or just the right sum. So that's something that comes out as well. This, in fact, is known as a sandwich inequality. I really like that name, because we've got the actual value sandwiched between an underestimate and an overestimate. There's one more thing that should be said here, and this will always be true. The difference between estimates, well, I don't have to actually work them all out and then subtract them. I can see that if I subtracted them, it's going to be, I'm going to end up, like they're all going to cancel, except I'm going to end up with y4h minus y0. So if you get asked for the difference between estimates, you only have to work out these slight differences that are going on with the areas, and that will just make things a little quicker. Okay, just very quickly, we've only done it for 4 intervals, but hopefully you can see how it might extend to n intervals, and I think I can fit it into this tiny bit of space. For n intervals, we're going to get h is equal to b minus a over n, and then the left hand sum, or the left sum, is going to equal h times y0 plus y1 all the way up to yn minus 1. I don't include that very end point. The right hand sum is equal to h, and now I don't include y0, so it's going to be y1 plus y2 plus dot 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 plus yn. Now you could write these down using summation notation, and you could write it really concisely. I'm not going to do that here, but I'll let you think about that. But there we go. That is a derivation of the rectangle approximation. You can hopefully see how it's come about. You can see why it's really nice and simple. Slight differences between left-hand sum rather, right-hand sum, and we can find out the difference between these estimates as well. And we've got this sandwich inequality in the mix as well. Okay, one other quick note. What if the gradient is negative? Well, it's all going to work out in exactly the same way, except this time we're going to get that the left-hand sum, or let's call it the left sum, that's going to be bigger than the actual value, which is going to be bigger than the right sum. Again, this is only going to work when the gradient is always negative. It doesn't have to be constant, but it's always negative. As soon as you get like a turning point going on, it all falls apart. So we're only looking at very specific curves. The formula are going to be the same. The difference is going to be this time y0h minus y4h because of the fact that this one is now larger. Okay, because you've got this extra bit here, and you're actually sort of missing this bit here. In this case, because the function reaches 0, actually, the difference will just be y0 times h, because y4 over here is simply 0. So actually, that's even quicker to find the difference between the sums. Let's see the rectangle approximation in action. So here we've got an integral, and I'm not sure if it's possible to write down an exact solution. I'm sorry, I think I should know that, but it's not going to be easy to do. If it's an x squared, we can use a trig substitution, but an x cubed, game over. Maybe not, but I'm not sure what it is. Okay, but we can use the rectangle rule to make approximations. So let's do that. We can find an underestimate and an overestimate. First of all, for 4 rectangles. So we're going to get that h is equal to 2 minus 0 over 4. It's just going to be 0.5. And I've got the diagram, so I'm going to use that to assist me. I'm going to start at 0. Let's do the left-hand sum to start with. Okay, here we go. That's going to be what we're actually calculating. And now let's write down a little table of values. I'm going to do it vertically today because I can sort of fit it in vertically, all right? That wasn't a very straight line. Okay, so then I'm going to get, I'm going to do 0, 0.5, 1, 1.5, and for the left-hand sum, I don't need 2, so I'm just going to leave that for the time being. Then I'm going to actually, no, I'm not. I'm going to work it out. Okay, and then I can substitute these into my calculator. I think I'm going to do it exactly rather than using a table. So I'm going to, first of all, when I substitute in 0, I'm going to get the square root of 1. Are there any others that easily come out? Well, when I do 2, I'm going to get 1 plus 8, square root of 9, which is 3. When I put in 1, I can quickly see I'm going to get root 2. So yeah, I can do those in my head. Right, I think I'll get a bit of help with the other ones. Square root of 1 plus 0.5 cubed. Okay, 3 root 2 over 4. And then if I do it with 1.5, root 70 over 4. Okay, so I can see the left-hand sum is going to be my underestimate. Left sum or left-hand sum, I think both are fine. Right, so then I've got my h. And you don't, this is the quick way of doing it. You could just do 0.5 times that plus 0.5 times that, but I've shown that we can do it all in one go. So it's going to be 0.5, 1 plus 3 root 2 over 4 plus root 2. I don't know what is going on with my pen today, I'm sorry. Plus root 2 plus root 70 over 4. Okay, stick that into my calculator. You should try this along with me to see if you get the same answer. Just be careful getting outside the roots. Okay, 2.7832. Which are probably round to 3 significant figures. We know it's an estimate, so there's no point in actually being really accurate. And then the right side. Okay, this is going to be so the first one's going to actually be really similar if I'm using the right side. But then if I use the right side here, it's going to look like that, and then like that, and then like that. So hopefully you can see the difference, and I'm going to get this overestimate going on. This time I don't use the 1. Okay, I'm actually using the right hand one as my first point, and that's going to be 3 root 2 over 4. I know in this case that's going to be really close to 1. It's just the nature of this curve. So it's going to be 3 root 2 over 4 . Okay, and actually it's going to be virtually the same, except I'm replacing 1 by 3. And all that's going to mean is that my answer is 1 higher, 3.7832. Which is 3.78. Nice one. We've used the rectangle approximation with 4 rectangles. We don't necessarily need to remember y0 plus y1, etc. But I hope it sort of naturally comes out that this is what we're doing, and that's it. Now find the difference in the underestimate and overestimate when 20 rectangles are used. This links back to something I spoke about before. You can see that the difference for this one over here is actually just 3 minus 1 times 0.5, because these are the only terms that are different. So for 20 rectangles, okay, this is part B, I suppose, I didn't label it, h is going to equal 2 minus 0 over 20, it's going to be 0.1. So now the difference is going to equal h, which is 0.1, and then I've still got the same thing going on. I've still got the same endpoints regardless of what h is. All the other points are going to be the same. They're going to be comparable in the two estimates. So all I need to do is 0.1 times 3 minus 1. And so my difference is going to be 0.2. I think I'm going to do that in just a little bit more detail. So the left-hand sum, I just want to explain where that came from if you're not sure. the left-hand sum is going to be 0.1, and then you've got y0 plus y1 all the way up to y19. The right-hand sum is going to be 0.1. We start with y1 plus y2 all the way up to y20. If I subtract them, the right-hand sum is bigger. Then they're all going to cancel out when I subtract. Like the y1s are going to cancel out, the y2s all the way up to y19s. But I'm going to get 0.1 y20 minus y0 left, and they are still going to be evaluated at B and A, which in this case was 0 and 2. So if I did that a little bit quickly, I'm sorry, but hopefully that makes it clear now. Okay, a final example on the rectangle approximation. We're going to look at quite a cool thing. We can make an underestimate and overestimate of ln 2 by suitably integrating y equals 1 over x. So I want you to pause the video and think, how could you do this? Well, there is a major clue in that it says to integrate 1 over x, so we need to remember that that becomes ln of the modulus of x plus c, but if we do a definite integration, we can get rid of that plus c. If I want ln 2, there's actually lots of things I could do. I could put in 2 and 1, because that would give me ln 2 minus ln 1, and that cancels. I could actually put in 4 and 2, and that would give me ln 4 minus ln 2, which again would be ln 2, or even actually anything that is double the other value. So 150 would also work. I actually investigated this, and the nature of the curve means you don't gain any advantage from doing these ones. You'll get exactly the same answer, in fact, for a number of rectangles, because although the curve flattens, the space between it becomes larger, and actually it cancels out exactly. So we're going to focus on just substituting in 2 and 1. Okay, that's the exact answer, and in fact, if we work that out, it is, I'm relying on my calculator, it is 0.693147. But how do we know it's that? How does the calculator know it's that? Well, we can use the rectangle rule to get some bounds, and so that's what we're going to investigate here. Okay, for us, right, let's just sketch the graph to get a feel for it. 1 over x looks a little bit like this, and then I've got my left-hand point. This is at 1. Okay, and it's roughly as a sketch, it's going to look like so. And this is 2 here, but I'm not going to use that one in my final answer. Now I see I've got a left-hand sum, and this is going to give me an overestimate. So the width is going to be 2 minus 1 over the number of rectangles I'm using. That's going to be 0.2. So it's going to be 0.2, and then I'm going to times by the function, so it's going to be 1 over 1 plus 1 over 1.2, etc. Okay, and then I don't include that 1 over 2, so I can put that on my calculator. It's not too bad. Instead of using the fraction button, I can do a little sneak method and just do divisions. Okay, and we get a decimal actually, which is not bad. But we get 0.74, and the thing is, it's not that close. It's not really worth writing it as a decimal because it's not a good decimal approximation. I get 0.7456. I probably shouldn't have said what the actual answer was. At the moment, we just know it's ln 2. We can see it's not a very good estimate, but it does give us an upper bound on ln 2. I mean, there's no denying it. We've used the rectangle rule. There we go. The right-hand sum is going to be very similar, but this time I don't use the starting point, but I use all the others. Okay, and actually this will just require us to go back in our calculator, although oh yeah, I've got it here. Okay, and instead of having 1, I replace that by 1 over 2. So very quick to do the second calculation when I put all the effort in, and I get 0.6456. And I can see that that's less than what I've got there. So I can write down that 0.6456 is less than ln 2, which is less than 0.7456. I think this one was a bit greater, so that's absolutely fine. And I've got a range of values of ln 2, however bad that is. Now we can actually do better, and you know, to some extent, this is the end of my example from the exam perspective. But in terms of finding ln 2, well, we could just use more rectangles, and we could do these calculations. Now, how could we do this calculation more quickly on our calculator? You know, we could obviously, like, if we didn't have a calculator, this would take a long time. But when people were first trying to find the exact value of ln 2, not sure they're using this method, but they could have used this method. How could we do it then? How could we simplify this sum out of interest? Well, we could write it as 0.2 and then a summation. So it's going to be 1 over, and then I've got 1 plus 0.2x. And I'm going to sum over, I probably shouldn't use x, I'm using x, let's roll with it. X is equal to 0 up to x is equal to 4. Okay, because my first term is going to be 1 over 1. My second term is going to be 1 over 1.2 when I put x equals 1 in, and so on up to my last term of 0.8. So actually I can do this really quickly. Now, why might I want to do that? Because what if we make it 100 rectangles? You don't want to be typing that in by hand. But for this, bear with me, h is going to be 2 minus 1 over 100. It's going to be 0.01. And then if I want to find the area, it's going to be 0.01. And then the left-hand sum is going to be 1 over 1 plus 1 over 1.01 plus all the way up to 1 over 1.99. I don't include that 2. So how can I put that into my calculator? It's going to be 0.01. Actually, pause the video and you have a think about this. It's going to be very similar. X equals 0. This time x equals 99. 1 over 1 plus 0.01x. And you can actually type that into your ClassWiz calculator. I can't show this on screen because I don't have the ClassWiz calculator simulator, but it's there. It's in the top right. You'd have to press Shift and X, and then you can get that summation button and fill it in exactly like I've just done here. So I'm just going to have a quick go at doing that. Okay, wowzers, I get 0.695653 Okay, I'll stop there. So that's going to be a lower bound. And then if I want my right-hand sum, it's going to be exactly the same again, but instead of including this 1 over 1, I'm going to include 1 over 2. Let's go straight to it. It's going to be 0.01, and then instead of starting with x equals 0, I can put exactly the same thing in here, but I can start with x equals 1. So that becomes my first term, and then I'm going to go all the way up to 100, which will give me 1 over 2 as my final answer. So let's figure that one out. This is good stuff. Okay, and I get 0.69065. So finally, I can write down that 0.69065, for example, is less than ln 2, which is less than 0.69565. Okay, so actually what I've shown here, I mean, it's not great, but you could see how you could improve it further. You could use 1,000. I've essentially proven that it's 0.69 to 2 decimal places. Okay, that's not great, but it's, you know, it's much more impressive than 5 intervals. The actual answer, remember, was 0.693. And so I suppose as a rough approximation, you could find the average of these two, and then you'd get, get even closer. Obviously, you kind of lose the bounds, but you get an average for it. Yes, there are better ways of estimating ln 2, but through quite a simple method, it's got to be said, finding the area of rectangles repeatedly, I think this is pretty good.